Good afternoon, everyone. I am Rosemary Palmaria with Miss Jean Carla Guara and Mr. Ronald Encinas. We will now discuss the cluster analysis. So, what is cluster analysis? Cluster analysis is a collective term for various algorithms to find group structures in data. Clustering is the task of dividing the population or data points into a number of groups such that data points in the same groups are more similar to other data points in the same group than those in other groups. In simple words, the aim is to segregate groups with similar traits and assign them into clusters. Example: suppose you are the head of a rental store and wish to understand preferences of your customers to scale up your business. It is possible for you to look at details of each customer and devise a unique business strategy for each one of them? Definitely not. But what you can do is to cluster all of your customers into, say, 10 groups based on their purchasing habits and use a separate strategy for customers in each of these 10 groups. And this is what we call clustering. Moving on to the subgroups of clustering. Broadly speaking, clustering can be divided into two subgroups. First is the hard clustering. In hard clustering, each data point either belongs to a cluster completely or not. For example, in above example, each customer is put into one group out of the 10 groups. Second is the soft clustering. In soft clustering, instead of putting each data point into a separate cluster, a probability or likelihood of that data point to be in those clusters is assigned. For example, from the above scenario, each customer is assigned a probability to be in either of 10 clusters of the retail store. So we also have types of clustering method. First is the partitioning clustering. This method is one of the most popular choices for analysts to create clusters. In partitioning clustering, the clusters are partitioned based upon the characteristics of the data points. So we need to specify the number of clusters to be created for this clustering method. These clustering algorithms follow an iterative process to reassign the data points between clusters based upon the distance. So the algorithms that fall into this category are as follows. K-means clustering. K-means clustering is one of the most widely used algorithms. It partitions the data points into K clusters based upon the distance metric used for the clustering. The value of K is to be defined by the user. The distance is calculated between the data points and the centroids of the clusters. So the data point which is closest to the centroid of the cluster gets assigned to that cluster. After an iteration, it computes the centroids of those clusters again, and the process continues until a predefined number of iterations are completed or when the centroids of the clusters do not change after an iteration. It is a very computationally expensive algorithm as it computes the distance of every data point with the centroids of all the clusters at each iteration. This makes it difficult for implementing the same for huge datasets. So moving on with the PAM, partitioning around medoids. This algorithm is also called as K-method algorithm. It is also similar in process to the K-means clustering algorithm, with the difference being in the assignment of the center of the cluster. In PAM, the medoid of the cluster has to be an input data point, while this is not true for K-means clustering, as the average of all the data points in a cluster may not belong to an input data point. We also have Clara, which is the clustering large applications. Clara is an extension to the PAM algorithm where the computation time has been reduced to make it perform better for large datasets. To accomplish this, it selects a certain portion of data arbitrarily among the whole dataset as a representative of the actual data. It applies the PAM algorithm to multiple samples of the data and chooses the best clusters from a number of iterations. Another clustering method is the hierarchical clustering. We have hierarchical clustering groups. The agglomerative, or also called as bottom-up approach. In agglomerative clustering, each data point acts as a cluster initially and then it groups the clusters one by one. We also have divides. Divisive, or also called as top-down approach. Divisive is the opposite of agglomerative. It starts off with all the points into one cluster and divides them to create more clusters. These algorithms create a distance matrix of all the existing clusters and perform the linkage between the clusters depending on the criteria of the linkage. The clustering of the data points is represented by using a dendrogram. There are different types of linkages. The single linkage In single linkage, the distance between the two clusters is the shortest distance between points in two clusters. In complete linkage, the distance between the two clusters is the farthest distance between points in those two clusters. In average linkage, the distance between the two clusters is the average distance of every point in the cluster with every point in another cluster. Another clustering method is the density-based clustering. So in this method, the clusters are created based upon the density of the data points which are represented in the data space. The regions that become dense due to the huge number of data points residing in that region are considered as clusters. The data points in the sparse region, the region where the data points are very less, are considered as noise or outliers. The clusters created in these methods can be of arbitrary shape. Another clustering method is the grid-based clustering. In this method, the data is represented into a grid structure which comprises of grids, also called cells. The overall approach in the algorithm of this method differs from the rest of the algorithms. They are more concerned with the value space surrounding the data points rather than the data points themselves. One of the greatest advantages of this algorithm is its reduction in computational complexity. This makes it appropriate for dealing with homogeneous datasets.
Evaluation of clustering. How clustering can be evaluated. Three important factors by which clustering can be evaluated are clustering tendency. Before evaluating the clustering performance, making sure that data set we are working has clustering tendency and does not contain uniformly distributed points is very important. If the data does not contain clustering tendency, then clusters identified by any state-of-the-art clustering algorithms may be irrelevant. Non-uniform distribution of points in datasets becomes important in clustering. Number of optimal clusters K. Some of the clustering algorithms like k-means required number of clusters K as clustering parameter. Some of the clustering algorithms like k-means required number of clusters K as clustering parameter. Getting the optimal number of clusters is very significant in the analysis. If K is too high, each point will broadly start representing a cluster, and If k is too low, then data points are incorrectly clustered. Finding the optimal number of clusters leads to granularity in clustering. Clustering quality. Clustering is done. How well the clustering has performed can be quantified by a number of metrics. Ideal clustering is characterized by minimal intra-cluster distance and maximal inter-cluster distance. Advanced cluster analysis. Cluster analysis is the task of segregating a set of objects with similar characteristics and assign them into different clusters. In this post, we will look towards some advanced topics of cluster analysis, specifically the four major perspectives of advanced cluster analysis. Number 1. Probabilistic model-based clustering, a general framework and a method for deriving clusters where each object is assigned a probability of belonging to a cluster. It is a useful framework for clustering data in a statistical context. This framework can be directly extended to the clustering of sequential data based on finite mixtures of sequential models. In the figure, the plot above suggests at least 3 clusters in the mixture. The shape of each of the 3 clusters appear to be approximately elliptical, suggesting 3 birobrate normal distributions. As the 3 ellipses seems to be similar in terms of volume, shape, and orientation, we might anticipate that the 3 components of the mixture might be homogeneous covariance matrices. Second, clustering high-dimensional data. When the dimensionality is high, conventional distance measures can be dominated by noise. Some of the major challenges we face during clustering high-dimensional data is many irrelevant dimensions make masked clusters. Distance measure becomes meaningless and cluster may exist in some subspaces. Third, clustering graph and network data. Cluster analysis on the graph and network data extracts valuable knowledge and information. Such data are increasingly popular in many applications. Graph and network data are increasingly popularly in applications such as online social networks, the World Wide Web, and digital libraries. A unique feature of graph and network data is that only objects and relationships between them as edges are given. No dimensions or attributes are exclusively defined. Number 4. Clustering with constraints. The area of clustering with constraints make use of hits or advice in the form of constraints to aid or bias the clustering process. The most prevalent form of advice are conjunctions of pairwise instance-level constraints of the form must link, or ML, and cannot link, or CL, which states that pairs of instances should be in the same of different clusters, respectively.